Good morning. Am I audible?
Good morning, Dr. Sir. Good morning. Yes, you are audible. Properly, you are audible.
एक्चुअली जो आज के जो गेस्ट है ना, जो स्पीकर्स जो हैं वो 10 to 11 वाले जो हैं उनको कुछ अर्जेंट मीटिंग आ गई है. So the schedule of this talk from 10 to 11 is shifted from 1 p.m. to 2 p.m. today. Okay. और 11 to 12 वाला है वो एज इट इज ही रहेगा आपका. वो टॉक होनी है आपकी जो अभी की जो टॉक है 10 to 11 a.m. वाली, दैट इज गोइंग टू बी शिफ्टेड बाई 1 p.m. ओके. तो 11 to 12 वाली टॉक जो है वो आप 1 बजे से ज्वाइन करें. एक्सपर्ट्स के कुछ अर्जेंट मीटिंग आ गई हैं. और 10 to 11 वाली 11 to 12 आपकी एज इट इज जो शेड्यूल था वो उसके अकॉर्डिंगली चलेगी. ठीक है सर.
Okay, fine, Dr. Sir. That means participants are requested to attend this meeting at 11.
So all participants are requested to attend this meeting on at 11 a.m. Okay, and this talk is going to be shifted from 1 p.m. to 2 p.m. today.
Fine, Dr. Sir.
So all are requested to join the talk from 11 a.m. today. Okay, and this talk is going to be shifted from 1 p.m.
Good morning, Dr. Pankaj.
Good morning, sir.
This is Dr. R.R. Sinha from Department of Mathematics.
Yes, sir. Morning,
Nice to see you here, sir.
Thank you, sir. Thanks, sir.
The time of the session is 11 a.m.
Okay, sir.
So we have few minutes. Let the participant join, then we will start this session.
Sure, sir. Sure. Okay.
Dr. Malik? Hello, Dr. Malik? Well, good morning to all of you. Am I audible to all of you properly? Hello, Dr. Malik. Am I audible to all of you? Dr. Paul, can you?
Yes, sir. Yes, sir.
Okay. So I hope that I am audible to all of you. So on the behalf of the organizing team of this short-term course, I welcome you all in the 4th day of this short-term course. Participants, today we have with us Dr. Pankaj Kumar Pal. So before going to start his lecture, his talk, I just want to introduce him. Dr. Pankaj Kumar Pal received the BTech degree in Electronics and Communication Engineering from Gulkar Kangani University in 2008 and MTech degree in VLSI Design from NIT Hamirpur in 2010 and the PhD degree in Microelectronics and VLSI from IIT Roorkee in 2016 under the joint supervision of Dr. S. Dasgupta and Dr. B.K. Kaushik, Electronics and Communication Engineering Department, IIT Roorkee. Dr. Paul has received doctoral medal, Director's Medal from NIT Hamirpur for branch topper in MTech in the year of 2010. After completing his PhD, he joined the Department of Electronics and Communication Engineering, National Institute of Technology, Uttarakhand as a teaching associate in January 2016, where later he joined as an assistant professor from May 2016 and currently serving there. His research interests include novel MOS-based device, FinFET parasitic extraction, semiconductor device modeling, and low-power SRAM memory design. Dr. Paul is also a reviewer of many international journals belonging to the various publication houses such as IEEE, IET, Elsevier, etc. Dr. Paul, are you ready to present your talk?
Yes, sir.
So I welcome you all once again, sir, on behalf of the organizing team. And it's over to you, Dr. Paul.
Yeah. Thank you, Dr. Sinha. Is the slides are visible to everyone?
Yes, you are audible.
Okay. Okay, so thanks for the introduction, Dr. Sinha. So as per the discussion with the organizer today, as you know that I am from the VLSI background. So today my topic, I will discuss about the FinFET technology, which is actually a basic device perspective. As you know that because in this STC is more focused towards the material and device perspectives. So now I will discuss about the basics of the devices in which today we are working. As you know that most of the microprocessors that in today's era that will be focused towards the less than 10 nanometer devices, and 10 nanometer is that much small that the first challenge and first thing that came in mind is how you can fabricate it. Because I'll give you an example that as you know that within a 10 minutes can you identify that how much our nail is increasing. So that is the device that we are talking about within that limit, that what is the increment in nail in 10 minutes, that the fabrication of device we are talking about. And that is a 10 nanometer or a 7 nanometer devices that we will discuss it. So in today's topic, today's lecture, these are the basic topics I will cover. One thing I just wanted to clear to you that I'll assume that you all know about the Mos Basics. Because most of the material and the devices that we use in ICs is basically based on the Mos devices. If any of you have any doubt during this lecture or during this talk, then you can interrupt me anytime, so that it would be better that I will clear it then, because we are dealing with a more advanced topic that we currently use. So, and because of the time constraint, I will not able to cover all the basic details. of basic Mos and all these things. So I will, in case, I'll try to cover each and individual part, but in case you will find any difficulty, you can let me know and interrupt me anytime. So these are the basic topics that I am going to cover. First, we will discuss about the motivation towards IC, and what the IC is. As you know, that it is kind of an integrated circuits, and from past 60 years we are dealing with these ICs, and because of this the technology enhancement in these ICs, or either you can call this as a material advancement, technology enhancement, in any of the things that we're talking about, it is ultimately reflected towards the ICs, and that ICs, it is very, very important, so that we can nowadays we are able to predict all the, we can do any form any task, like palm top is there, some variable smart devices are there, variable specs are there. So all this is all because of the advancement in this ICs. So first we will give you, I'll just give you a basic motivation, that what is the motivation behind this ICs, and then we will discuss about a very important law, that is a Moore's law. I think most of you have already heard about it. And then we came to the scaling, and which is actually the main workforce behind the today's ICs and all the processors, memories, and all these devices that we are looking about. Okay. Then we can go towards the advancement, like in SOI, double gate, and the main topic of this today's talk is actually the FinFET devices that we currently use in our systems, in mobile phone, today's mobile phones. Like most of you heard about the Snapdragon processor, that is all fabricated and on the 10 nanometer FinFET devices, and some of the Snapdragon processor also fabricated with 7 nanometer FinFET devices. So what the FinFET is and how this journey towards the FinFET, and presently the research is going on beyond the not only the 10 and 7 nanometer, because all these devices are commercially, all these ICs are commercially available to us. But now we will look forward that in next few years, where we be there, and what is the role of materials, what is the role of device architecture, what are the different roles that we incorporate in today's era. So as of now, we cannot say I am working only on the device part, I don't know anything about the materials, I don't know anything about the other stuffs. But in today's era, we know actually all the things, and if we know all these things, then we are going to embed everything, so that we can find a better solution from some of the performance parameter, that may be in speed, that may be the chip density, that may be the power or energy part. Okay, so that perspective we will discuss about it. So I think all of you have already heard about the in basic courses of sciences or the engineering background courses. So you have heard about the Gordon-Moore's law or the Moore's law. And what happened in that, Gordon-Moore is nothing, he's actually a co-founder of an Intel corporation, and that we know that it is a giant industry who makes the today 90% or 95% of the today's microprocessor. And all these microprocessors are very popular because most of them are the general purpose in nature. And what is the story behind this? Because the Gordon Moore, who is actually a co-founder, as I already told you, and in 1965 he wanted to set up a new industry. All these, most of the researchers, whether it's Robert Noyce or all the IC's researchers, they all coming from the AT&T Bell laboratories, and when they see what is the market capitalization, what will be the they thought about it, what will be the future of the electronic industry. When they thought about it, then they say that yes, we can work on it, because we know, and most of the part at that time, we are talking about in 1960s or 1965. So at that time they know about it, what will be the future of electronics industry. So most of the researchers who anything knows about the semiconductor industries, they wanted to set up their company. So as you know that whenever we are going to start a new setup, then first of all we will do some market research, and the same thing has been done by the Gordon Moore. So we wanted, as you know, that he's a co-founder of an Intel corporation. So he did the same thing. So as you know that in 1956, the first IC will came into the existence, and that hardly take 4 transistors. As you know that what the transistor is, or you can say whenever we are talking about any circuitry, the basic part is some transistors or some passive elements, whether it may be a resistance or a capacitance or all these things. So by whatever be the output that we want, whether it's an amplification, whether it's an oscillation, whether we wanted to make some gates, adder operation, any operation that we wanted to perform, and in that way there is no need of doing some amplification, there is no need of doing some making some adders or subtractor. The main concept and the main hurdle that we have encountered in 1960s is actually to do some mathematical calculation. Can at that time we have a device that can do some mathematical operation, and that mathematical operation which is not feasible to do quickly by some hand calculations. So that is the main motivation. We wanted to do some mathematical operation which is not easy. So we wanted to make some devices, we wanted to make some machines that can perform these tasks in a short time or in a less time. Okay. So based on that, the Morse will predict whatever be the existence after the existence of IC. He just noted that in past 5 to 6 years, what will be the development in the IC. Then he noticed that after every 2 years, the number of transistors in any IC would be doubled. Okay. Later on, he will change, because 3 times the Morse have changed their law. That is why I have mentioned over there then 18 to 24 months, because it is not clear whether because in early days he would predict it to 12 months, the chip density would be double. Later on it will be stick to 18 months and then 24 months. So that is why he just study everything, and then they come to a conclusion that every time and every year the number of transistors would be double. Like in this case, there are some pictures looking over there. In 1950s, only single one transistor is there. In 1960s, some detailed quad gates are there that have 16 transistors. As you know, in 1950s to 1960s, only 1 to 16 transistors we can come up with. But as we keep on moving forward, 1970s 8-bit microprocessors that have 4500 transistors, and currently in 2010 and 2020s we were using the processor that is i7, i9 processor that have a billions of transistors. So how it can be feasible? How it can be feasible to make? Okay. What is the basic workforce behind this? As you know, why I'm concerning towards more number of transistors to be embedded in an IC, it is all because you can do any task when you have hardware. Let it be, I'm taking an example, suppose you have 4 transistors. What maximum, by using 4 transistors, what maximum circuit you can make? You will hardly go with an inverter or a basic AND gate and a NAND gate. But if I'm giving you a number of transistors and I'm giving you a freedom to use millions and billions of transistors, yes, you can make any kind of an operation. You can design any kind of a circuitry that will be able to do the lengthy or a complex task. And why? What is the requirement of this complex task? Yes, because you wanted to do all this calculation very quickly. Like I'm giving you an example. Suppose we wanted to forecast when the cyclone will come, when the tsunami will hit the bank of that sea. So that all this calculation, you need a very good, you have to do this calculation very fast, because if you are doing the calculation, there are lengthy equations are there, so you have to do it very quickly. And this is the basic workforce behind it. Ultimately we need the speed, we need the functionality, and to give the speed, to give the functionality, we have to require more number of transistors, or not only the transistor, we have to require more number of circuit elements, that may be resistance, capacitance, transistors, and all these things. So this is the basic workforce, and that's why in 1965 Gordon Moore published his paper in which he mentioned that the number of transistors, depending upon their study, because he wanted to set up a company. So based on that, he had just predicted that the number of transistors on a chip would be doubled every 18 to 24 months, and that will become a very popular thing, very popular article, and that later on it will be considered as a Moore's law that we will remarkably follow. And there are some advantages associated with this Moore's law. Not only if you are using the same chip, like in a layman style, if I just elaborate it to you, this is the basic chip area that I am already giving it to you. And you can also take another example. Suppose a land area is given it to you, and that is all up to you. Whether you wanted to one room in that land area or you wanted to 2 rooms in that land area, that is all up to you. If ultimately the major cost is the land. Okay? So major cost is the land. If you wanted to make 100 rooms or in that land, whether you wanted to make different floors or flats, that is all up to you. So per flat cost would be reduced, because as I already told you, the major cost behind this is basically the land. See? So more functionality you can give it to this circuitry. Similarly, there is a chip area. If you wanted to make 2 transistors out of that, you can give limited functionality, but the transistor per transistor cost would be increased. So not only we are giving the functionality to by incorporating more number of transistors to a chip, but additionally we will reduce the cost per transistors. We will reduce or we can also enhance the speed. Okay? So these are some of the benefits associated with the Moore's law. But how we can do so, and this is the one of the picture that we will look about. This is I think if any of you have learned about it, this is an Intel 4004, which is actually a 4-bit microprocessor, and that will be fabricated in 1971. That only have 2300 transistors. That gives you only a flexibility to add 2 numbers only, and that number will be only of 4-bit. But as of now, in today's era, you have not only in today's era, in actually 2001, this is a 42 million transistors processor is there, which is a Pentium 4 processor, and you can do any kind of calculations like Fibonacci series. You can find factorial, you can watch movies, you can do any number of tasks in that way, and multiple tasks you can also perform, and that is all because of the Moore's law. Most of the industries have marked it as they will consider this Moore's law as a benchmark to go for the technology enhancement. And because of this, and what is the basic workforce, how you can do this thing, that you have a limited area, and how you can incorporate more number of transistors in that limited area. This is only possible if you reduce the dimension of the transistors or dimension of the elements. Okay? And that thing we used to call this as a scaling. Scaling is nothing in our area, in microtronics and VLSI domain. Whatever with the scaling that we are talking about, we are concerning towards the reduction in the number of transistors. If we have an area, let it be same example is there. Suppose I am giving you a dimension, and that dimension I told you to make 2 rooms in that land area. Take it in that carpet area. So that is up to you, whether you wanted to divide in that way or you wanted to divide in that way. It is all up to you. But now I'm again told you that you have to design an 8 room in the limited space. How you can do so? Definitely the room size will be reduced, and this is the only feasible options you have to do so. So if Moore says that the number of transistors in every year would be doubled, then what you have to do, you have to make that your technology will be so advanced so that you can reduce the number of dimension, you can reduce the dimension of your transistors, so that you can incorporate more transistors, get more functionality, and then more speed. You're getting more speed. So this is the basic workforce behind all these things. That is the scaling. And what are the different advantages you got? That is, as I already told you, that the functionality you are getting the faster transistors are there. So overall, you are getting the speed, and you can incorporate more number of transistors are together. But yes, it would be difficult to do all these things until and unless our technology will be so much advanced. So this is the basic implications of the scaling. How we can do so? As of now, we will not discussing in detail, but there is a detailed things about it, how we can do so, what are the benefits, what are the ways to scale the transistors, what are the ways to scale the individual element. I'm not going into detail into that part, but as of now, today I'll just elaborate you what are the different implications of the scaling. As simple as that. So these are the different implications, like the performance is improved. Performance in this part, I mean to say that the speed is increased. Because how we can do so? I'll just give you an example. Suppose there is one base there is a starting point and there is an end point. So I will just define this as a starting and end point. Suppose I'll just told you that one person is sitting here and he wanted to finish this race. This is a starting point and end point. So suppose let it be this is a 100-meter race. So within an X time, it will cover this 100-meter race. Now I just wanted to tell you that how can I enhance the speed? So in that case, the speed, or in semiconductor perspective, my main intention is to send the electron from this point to this point. Because whatever I am talking about, the person that is in the device or material perspective, the main intention is to send, initiate the electron. So when the electron will start from there and when it will be reaches to there, that is the time that we talk about, that it will start its race and that at the destination point it will finish this race. So that time we are talking about. When this race will be end up, then we are talking. Let's say that this would be the total time, and that would be the current actually. So like the dq by dt in general, the charge or the time within the specified time, how much charge will be passed from this side to this side. Okay. Now suppose I told you that I just anyhow I wanted to enhance the speed. How can I enhance the speed? Because electron is, we don't know that there are so many number of electrons from where they are moving. There is a velocity is there. There is a maximum material property is there that we talk about the mobility. So beyond that mobility, that will signify the speed of the devices. That without modulating the mobility, we cannot say we can increase the speed. So the only thing I can do is just by reducing this dimension. So instead of now, earlier the electron will race from 100 meter, now it will race it to 50 meter. So from that perspective, we can say now it will complete its task within less time. Definitely, if you told me to go for the 100-meter race and my speed is fixed, and if you told me to cover it only 50 meter, then definitely it will take less time for me. Okay. From that perspective, I am calling this as yes, the speed will increase, because my main intention is to finish my task. If the task is finished within 15 meter, then definitely it will be the speed. So that is why we are saying that the performance would be increased. Similarly, the cost is increased, improved cost. I am calling this as improved cost. As I already told you, you have a land area. If you wanted to make only 2 rooms, then per room cost would be definitely high. If you in that land area, if you are making 10 rooms, 20 rooms, definitely per room cost would be less. So you can sell more. That will be the cost will be increased. Okay. But there are some certain challenges are there, like interconnects, powers. Whenever you are incorporating more number of devices together, when all the devices are on, then there is a heat dissipation. And because of this heat dissipation, what will happen? There may be a chance that the IC will burn out. And you will notice this thing. 10-20 years back, you will notice whenever we are using this desktop or these laptops, there is a cooling fan is there. As of now, in all the laptops, there is a cooling fan is out, but you are not heard so much voice. But at that time, there is a lot of issues are because of that. Yes, my system is not working because of it will be getting heated. Okay. So this is all because of the power dissipation. If you are compacting everything in a very limited area, that we wanted to do, because ultimately we have to enhance the functionality. So to enhance the functionality, we have to incorporate more number of transistors, more number of elements in a circuit. But each individual element will transmit some power in form of a heat, and that heat will be deteriorate or that will damage my IC. So what is the purpose of that? So this is an important parameter that we have to look about. Okay? And there are certain, means simple as that, whenever you wanted to do something, whenever you are getting something, you have to be pay something. Okay? So this is the basic thing. After each and individual component, this is my opinion, I'm not coming from that. Whenever we are using some alternative to that, it will give me some advantages, but along with that advantage, it's come up with several challenges, and that challenges we have to take care of. Okay. So this is the basic part. So these are the benefits and some disadvantages that are there. Benefits, we can easily take it, and disadvantages, we have to work on it because we have to improve it. So there are some certain issues are there. Now we will discuss. As I already told you, that what I wanted to make. I wanted to make a device that is of 10 nanometer. What is the size of an atom? It will have 1.1 nanometer or in 1 angstrom range, 5.5 angstrom or 0.5 nanometer. Okay. So can I make a devices that can have a range of atomic range? It will, whether it is feasible for me, whether my technology is that much developed, how can I make this thing? Because this Moore's law will be defined in 1965, and currently we are living in 2022. And then we have to look about how these devices will work as of now. Can we follow the same rules? This is the basic hurdle. And from past 10 to 12 years, we have continuously heard that yes, Moore's law will not be able to follow. Why? The major reason is that because we are approaching towards the physical limits. This is a simple example is that suppose I'm giving you a paper and I just told you that this is a paper I have and you just wanted to fold it. In every 10 minutes you have to fold it. Definitely there is a point where you have to face at a certain time, after some certain time, after giving so much folds, then there is a time then you are not able to further fold it. So this is the reason. This is the basic physical limit. You cannot hold it thereon. Similarly, that if you are continuously reducing the device dimension and you are approaching towards the atomic scale, then how can you reduce the device dimension beyond the atomic scale? This is the minimum dimension. Atomic dimension is the minimum dimension that you can go with. So there are some physical limits are there, and because of approaching this physical limit, it would be very difficult for us to further scale down the things. If we cannot further scale down the things, then how we can enhance the speed, how we can go with the power, how we can making a devices that will be easy, how we can make these variable devices, palm tops and all these things, then again it would be an issue for us. Okay. So there are some certain challenges are there that we have to take care of. In technical terms, we are calling in lot of things are there like velocity saturation. Velocity will be saturated after a certain time. This is kind of a similar example. Suppose you are driving your bike or a car, then you can see there is a defined limit over there. You cannot take it more than 220 km per hour. Okay? So this is the basic limit. If even though you are continuously pressing your accelerator, but you cannot go beyond 220, or if you are running a bike, if you are driving a bike, then you cannot go it with 150 or 180. Then what will happen? There is everything, there is a limit, and you cannot cross that limit. So what will happen? Again, because of this limit, you cannot further do the things. So what are the different ways we can do so? The ethic of the development that we are taking is, and one thing you have to keep in mind, we are doing all these things starting from the discovery of electron till today's area. There is no such single solution that will be applicable that will give you the maximum all the benefits. Okay? So there are some certain challenges that you have to take care. There is no such solutions is there. One, you will change one material to the other material. Definitely that material gives you some flexibility, but along with that flexibility, it will give you some challenges as well. So what you have to do now, your task is to remove that challenges. You have to work on to reduce these disadvantages and work for it. Okay? But continuously you have to do the certain improvement. So these are the different things. These are the different technical terms are there. So I'm not going to discuss it. So these are the different terms. So overall in general, as ITRS has already proposed, or it's in kind of a team that they're all based on which all the semiconductor companies are working towards it. So ITRS will set a benchmark for all the semiconductor industries that yes, for further next 5 years you have to work on that materials, or you can work on, or you have to get that much of performance. So these are the reports that is coming from. So based on the ITRS report, they are proposed 2 strategies. First strategy is to implement new material as a performance booster. You are using the same MOS devices, you are using the same transistors, you are using the same resistance and capacitance, but there is a limit, there is a physical limit. You cannot increase the mobility of a silicon, you cannot increase the mobility of a maximum mobility, the mobility of a germanium. Then what you can do? If you cannot increase the mobility of a silicon, that is 1430 centimeter square per volt second, then what you can do? Who will force you to use the silicon? You can go with germanium that have a higher mobility. You can go with them. Nowadays, currently we are working, or the researchers are looking a perspective towards the germanium, not germanium, graphene, CNT, carbon nanotubes, that will give you an mobility in terms of in lakh. So who will force you to use this 1500 mobility devices? You can, if you wanted to enhance the speed, you can forget about the silicon. You can go with the graphene and the CNT. So that type of a performance booster you can do. But yes, you have to be very sure. You have to be not only you just have to improve the devices. You have to think about it. Then these devices, what will be its implications? Like currently, I'm using my printer. And in that printer, you all know that whenever you procure some printer, there is some drivers are there, some software and hardware drivers are there. And if you want this, all these materials, like all the hard disks and everything, it is by you have fabricated in based on silicons. If you one day you thought about to improve the performance and you wanted to replace silicon and move to the graphene devices just by enhancing the speed, what happened to the previous devices that we are talking about? They are completely useless. You cannot use my printer because we don't have an available software. We don't have an available operating systems. So can we do the sudden changes? No. Okay. So we have to make an optimization whether we are going what performance booster we can take and how this will be impacted the society. Okay. So there are so many things are there. Like as I am giving you an example, instead of silicon, you can go for the germanium that have a higher mobility. Otherwise, you can go for the graphene device or carbon nanotubes that will give you a mobility in terms of lab. Okay. So that much mobility means you can understand that around 70 times high speed will be given by the CNT device, 70 to 100 times, because the mobility is ranging from 1 to 2 times. Okay. But and as compared to the silicon device, then why you are wasting your time to the silicon device? But yes, there are a lot of commercial devices are available on the silicon. At a night you cannot discard everything. Okay. So that is why some performance booster you have to think about it. As I already told you, there are so many things are there, like high-K dielectric metal gates. This is the in 2001. This thing has already been changed in Intel, and you didn't notice anything about it. In 45 nanometer devices, they most of the time, in actually what the MOS is, I think because in earlier part I have already told you that I assume that you already know about the MOS devices. MOS is nothing but actually a 3-layer device. It is a metal oxide and a semiconductor, and that oxide is of SiO2 or silicon dioxide. So on top of a silicon, we are going to grow the silicon dioxide and then metal, so that we can control the charge flow with the help of electric field. Now, what will happen? This SiO2 device, this is act as like a parallel plate capacitor, and if you are reducing this dimension, the capacitance will increase. But how much you can reduce the dimension? As I already told you that in 1965 we have a dead dimension, and in 2022, because as per the Moore's law, we told that at every 1 year or 2 years you have to reduce the divide dimension, and it's 60 to 62 years. Or further we can reduce the dimension. Can't we approach it to the atomic level? Yes. So how we can do so? How we can maintain this capacitance? So because of that, we have used some high-K materials are also there. So instead of SiO2, which have a permittivity of 3.9, we can go with IK devices like HFO2 that have a permittivity that ranges from 22 to 25. So within the same capacitance, you have again a higher thickness. Now you have a further scalability, you can do so. Similarly, these are some of the examples are there. My main intention is to tell you, either you will go within, you will use the same structure and use some material, performance boost, that will be act as a performance booster. Like if you wanted to enhance the mobility of a silicon, go for the straight silicon that have a high mobility, go for the high mobility channels. All these things are there. So at every point, researchers have leave no stone to work on any of part of the transistors, whether it will be source or it will be drain, gate engineering, channel engineering, every part they will focus towards it and come up with a new solution. But again, as I already told you, getting any solution will also come with some challenges. Okay? So these are the second strategy is to develop the new device structure. Forget about the Mos. Who will want to use the Mos? You can go with a new device structure that will give you the better flexibility, that will give you the or you can say the I'm using the different structure, different kind of structure. Like as of now in today's era, as you know that most of the devices that we currently use are working on silicon devices, which is actually a charge-based material. But currently, there are some devices are there that will be on spin base, that will be on optical devices are there. So, which is not only on the charge-based devices spin, you have to control the current with the help of the electron spin. Okay? So these are the some different solutions, some novel solutions are there that we work towards it. Definitely it will change the complete path, but as I already told you, we are not thinking to change it overnight. Lot of research from past 10 to 12 years, lot of research has been carried out on CNTs or different devices. But currently we don't have an active commercial devices that will work on it. We know anything about it. As from the material perspective, we know all things, all know anything about the graphene, what will be the mobility, how this will be change its performance, how would be the its impact with the temperature. But still, we are not able to commercialize it because a lot of issues are there. Variability, reliability issues are there. Whether we are going to make it comfortable for, we cannot change it overnight. Okay. So these are some of the examples. And the second strategy proposes this one, as I already told you, like Mos devices. We are using some novel devices to enhance the performance. Okay. And my today's topic will only be based upon these devices. So FinFET device, silicon nanowire, double gate, all these devices are there. Okay. So now we came up with this thing. So as you know, this is a Mos device, and this is a metal layer, this one is an oxide layer, and this one is a semiconductor layer. And there is a source and drain is there. This is the source, this is drain. The main intention why I told you that there is a starting point, there is a destination point, there is a race. Yes, there is actually a race. The electron will have to travel from this point to this point. And this is the task that I have to perform. But yes, how can you can call this as this is one side of a river, and this is the another side of a river, and this is the river flowing in between. Okay. How can I move from this side to this side without making a bridge? So first of all, with the help of this gate, with the help of this capacitive action, I have to form a bridge. Then only I will be able to cross it. As simple as that. Okay. So, but as we keep on reducing this device dimension, what will happen? There are some certain parasitics are there. These are the capacitances are there, some parasitic capacitances. My main intention is to flow of charge from the one end to another end. But these capacitances will now, as we keep on reducing the device dimension, one thing you can call this as parasitics. And parasitics may be of any type. Like suppose I'm calling you, there is a metal, this metal layer is there. So because of this metal layer, not only this capacitance there are some outer fringing capacitances also there. At that time, when we are talking about in 1980s or 1970s, this fringing capacitance, definitely they have this interparasitic capacitances, but there, as compared to this one, this has a very low value. But what happens today is this will be in comparison with the main field. Okay? And this is the basic problem that we are talking about. So that is why it's a novel devices. Why I am talking about the SOI devices? Because in 2012, when I am doing my PhD, there is a lot of debate has been going through. After Mos, after the Moore's law, what we have to opt? Whether we can, some of the industry giants like ST Microelectronics, Cadence are there, they will move towards the SOI. They told that the SOI will be the future of this ICs. And some of the devices, that is Intel, TSMC, all the giants, they told that no, the multi-gate or the FinFET devices are new future. And definitely, because now, because it's a matter of last 10 years, so now all this lead will be taken by the FinFET devices. Because who will be getting the first device that will definitely take a lead, and Intel will get the lead to introduce the first commercial devices that is based on the FinFET devices. Okay. And that is why, as I told you in starting of this lecture, like a Snapdragon processor, it is all completely based on 10 nanometer FinFET devices, 7 nanometer FinFET devices. These are the things. Okay. So I'm giving just an example to you then how another device that is an SOI device will be work on it. It seems to be a very common as the basic MOS. But why I'm calling this as a normal MOS device and why I'm calling this as an SOI device is all because now you look, there is a capacitance in between these two nodes. So these capacitances are called as the parasitic capacitances. And capacitances is like a bucket. As the capacitances will increase, the parasitic capacitance increase, the size of the bucket will increase. If I told you that you have to fill a bucket by water, then how much time it will take? And that is actually my speed is. In general, we talk in that way that how much time it will take to fill this bucket or to empty this bucket. So as of now, I'm just take it as how much time it will take to fill the bucket. If I'm continuously increasing the bucket size, definitely it will take more time. If it will take more time, that means what will happen? Your speed will be less or your delay would be more. Okay? So what we want, our device will show a minimum capacitances. Minimum capacitances mean minimum bucket size is there. That means we can fill it is very easily. Okay? So this is the main reason. So main intention, and as the capacitances will less, if the capacitances will less, then you are getting a high speed device. And this is the main advantage that we are talking about. In all the cases, we want a high speed device. I have given you an example as well. Why we want a high speed device? Because ultimately you have to calculate when the tsunami will hit the sea, when the cyclone will hit any part of the country. So you have to do the fast calculation, and that is why you need a very high speed devices, and that is why we use this supercomputer and all these things. Okay. So this is the basic reason. So how you can reduce the capacitor? Yes, easily you can do so. Just put a SiO2 over there, or separate this part with respect to this part's substrate, because most of your current is flowing only in this direction. So why you are carrying all these things? That will give you an extra capacitances, and this is what we have to. This is in box layer is there, but it means we wanted to separate it out, and because of that, the internal parasitics will become reduced, and because of the parasitic will become reduced, we are getting high speed devices, low power devices. Why low power? Definitely the capacitance will reduce, so overall the power dissipation will also reduce. Okay. So these are the basic advantages that we are talking about. And currently, please note that I am not saying commercially most of the industries will focus towards the FinFET device, but as of now, any of the radiation hardened device, any of the material perspective, military applications, we are using this SOI device. Currently, we are working on it. Most of the defense industries, most of the aeronautics engineering, they are using this SOI devices. Why? Because there are so many advantages associated with it, and that advantages will be the low soft error, and that will make us this is a radiation hardened device. So whenever you wanted to send any device, any rocket to the space, then you need a radiation hardened device, because you know in space there's a lot of radiations are there. The temperature is completely goes in different directions. So what will happen? Your chances of device failure is a very, or you can say there is a very strong chance of your device failure. So definitely you have to use this device. So as of now, from the defense perspective, we are not saying that SOI would be. We are currently using it. Okay. So that is why I just wanted to tell you basic about it. There are some other advantages as well, like latch-up problem is there, radiation, all these things are there. Speed and power is enhanced with respect to the basic MOS devices. So all these things is there. The soft error, what actually happen is that this whenever you are using some MOS devices, you know there is a substrate is there. It's a silicon substrate is there, and whenever the alpha particle will hit your devices, then there is a generation of electron and hole pairs. And when the electrons or holes are generated, excess electrons and hole pairs are generated. So this will increase, all the electrons will come in at this side, all the holes will go to the another side. What will happen? There is an excess current, and that excess current may lead to deteriorate or failure your device. So that is why we are saying that in space, whenever any of the device will be sent, any of the IC will be sent, it will not work properly. Why? This is the reason. Because lots of radiations are there, and that radiations will actually causing for the error. In this case, if the why we are calling this as an error, soft error, because as of now we thought that most of the time the device will not be failure. It may lead to failure, but if there is a changes shown, and that change is shown, we call this as an error. Okay? Like error is there, the device is not is in failure state. So this is the two things that we are talking about. Okay? Are you getting it? So how we can do so? As you know, in this case, what we have done in SOI, we have separated out the box layer. The substrate is separated out from the box layer. Yes, any doubt is there? And because of that part, only this will be exposed to the SiO2. So as compared to that part, less number of electrons and holes are generated. So less changes is there. That is why we are saying the radiation hardened device. We are not saying that we are completely immune to the radiation. Hardened means we can reduce the impact of radiation onto that devices. So this is the basic part. Okay. So there are other advantages as well, and this is why I'm calling this that it is still the CMOS is using. Although it is commercial, for commercial perspective, we are not using the SOI devices, but from the military and space perspective, we are still working on it. Space devices, that is for the military and space application. And this is the basic part. And you know that defense is a separate thing. You cannot compete within commercial budget as well as the defense budget. Defense budget is completely very high. You are getting the better revenue, but yes, you have to be gem in that part. Okay. So there are very less few companies are there who are working on SOI, but that will be a leader, because most of the revenue they are related for the defense applications. Okay. So these are the things. Now, as I already told you, that one feature would be in SOI. The another feature is that what else we can do to enhance the performance, and this is the basic limit. We use bulk devices, or specifically the MOS devices, at a level of 32 nanometer. And at that time, because these slides are quite old, so at that time we assume that below 10 nanometer, we definitely have to come up with a new solution. We are no longer using the silicon-based devices. We can go for the CNT devices or a germanium-based device, or some compound or hetero devices are there. Photonics, optoelectronics we can go with. Okay. So there are large field of devices that we do. So there is a large gap. What devices, what kind of an IC we can make in between, that lies in between 32 nanometer to 10 nanometer. Why 32 nanometer is the limit? Because at that time, leakage current is as equal as the drive current. If you are not able to, what is the leakage current? The current will be flowing in the off state. And what is the drive current? When your device is on, the current will, and the current flowing in on state. If you can identify that the current is flowing in on state and off state is same, you cannot identify, you cannot even easily switch off your devices. So do you want any kind of a device that you cannot even identify, that will never switch off? No. In electronics or in any of the domain, the controlling is the main perspective. We want and all the things, but we know the switching capability has to be with us. It is up to me when I wanted to switch on the device and when I wanted to switch off the device. This is all because of it. But because of the leakage, because of all these parameters, we know that at 32 nanometer part, we cannot extend it beyond, because of the physical limit, because of all the scaling implications, power issues are there, a lot of things that we have discussed earlier in the scaling part. Okay, so how we can go to? So the first proposal has come up with some of the researchers. They said, why don't you use, as of now, you are actually controlling this channel. Why I am calling this a channel? जैसा मैंने आपको बताया, like in this case, there is a source is there, there is a drain is there, and my main intention is that the electron will flow from this side to this side. So this is a starting part. For those who don't know anything about the MOS devices, you can consider it as a source or a starting point, and this is the destination of a race. So electron have to take that race. Okay? So my intention is to send electron from this side to this side. Okay, so this is the starting point, this is a destination point. Okay? So how can I fill this? This is a channel through which it will, this is a racetrack or a channel. Okay? Now the electron, what you are doing, so the electron will move in any of the direction. And how you can, if you are moving zigzag in zigzag position, how you can quickly go to this point? If you are running on a racetrack and you are revolving round and round, how you can complete your race within a less time? Okay? So this is again a big challenge. Then how we can do so? You can confine the way. You can confine the way of the silicon, and then how you can do so? You have to apply electric field from all the parts. Okay? This is the way, so that it will not, you will confine the electron not to go in this direction. If you reduce the device dimension, or in other words, I will call this as if you can control the silicon movement so that it cannot move in any other direction, it can go directly straight. This is the case. So we have to make it confined. And how we can make it confined? Control it from all the other parts. And that is why earlier we are using a single gate devices that will control the flow of electron, like in case of a MOS device. There is a gate channel is there, and you are controlling the silicon electron moving from this side to this side, from top side. But how it may go to this direction, it may go to this direction. But if you can make another gate in that way, so that there is a confined path is there. That is why the concept of double gate has to come into picture. And this is the basic double gate concept. How we can make it, this is another thing. What are the process complexity that we have to face, another thing is there. But yes, if this is a simple example is there, actually the father of all these devices is the Chen Ming, who is an R&D director of the TSMC, Taiwan Semiconductor Manufacturing Company, who actually coined both these the devices, that is a SOI or the FinFET device. So he explained in that way. Suppose you have a ground, and in that ground you have a grass, and you leave one pipe is there with the flow of water. So water will move from one end to another end. How you can control the you restrict the flow of water. So either you are going to press it from the top side, or the another way is you are going to press it from both the sides. Then only you can able to flow of water, restrict the flow of water. And this is the example they have given. From that perspective, they said, जैसा मैंने अभी आपको कहा कि you have to restrict, you have to confine the movement of silicon. उसको इधर उधर जाने ही नहीं देना है. हमें हर साइड से, from all the sides, we have to confine the dimension. And if you can completely confine the direction, if your electron will move only in one dimension, not in another dimension, only moving in extra dimension, not in y and z, then this kind of a phenomena we used to call as a ballistic transmission, ballistic transport. Why ballistic? Might be you have heard about the bullet thing. Whenever we are firing from a bullet, or if anyone of you is firing from the bullet, then you see the bullet have a very high velocity. Why? Because you are leaving the bullet, your gun is forcing a bullet with a very high force, and that force they will not moving in another direction. If it will move in another direction, your point of intersect, or you can say आपका निशाना चूक जाएगा. ठीक है. So this is kind of a ballistic transport is there. Definitely you are reaching to your destination point at a very less time, and that's why your speed will increase. So this is the basic advantages. So either you can go with a single gate device in, and if you wanted to improve it, make it a confined thing and make a double gate device, and that will give you the lower junction capacitances, means parasitic capacitance. This will be increased, the speed will be increased, okay? Current will increase, and the gate capacitance. This is a good capacitance, because two type of capacitances we are talking about. One is a good one, that is a gate capacitance, which is actually responsible for increasing the current. And the parasitics that we are talking about is in bad capacitances, which is actually deteriorating. Okay, so our intention is to reduce the bad capacitances. I should not call this as a good or bad, but actually parasitic capacitances, my intention is to reduce the parasitic capacitances. Okay, so there are so many advantages offered by the double gate transistors. But apart from all these advantages, are we able to fabricate it? Okay, can you make a device? Can you make a device on a sheet of this is kind of a wafer sheet. Okay. Can you make a device on top of that, and you have taken terminal from this side? Most of the devices are planar in nature. Planar in nature means they are taking terminals from only single plane. Okay. Anyway, you have to put some device into that one. You cannot make a device that is suspended freely in the air. You cannot make it. So how you can make these planar devices? Okay. So again, concept is good, but it is not a feasible approach to make it. And there are a lot of research has been carried out. This is one of the things that I'm talking about. Okay. As you know, this is kind of an SOI devices, single gate SOI devices. One gate is there, SOI devices. Whenever you are applying some potential, because of this fringing, the electric field will move from this side to this side. And again, the other electric field, which is coming from the back of the side, will be moving to this one. So what will happen? This drain electric field, or the destination electric field, it actually controlling the channel region, and that is part we are calling this as a case. हम बोलते हैं कि जिसका काम उसी को साझे. That means कि whoever is responsible for the task, that task has to be completed by himself. So this is the task. The task of a gate is to create a channel, and the task of a drain is to taking the charge carriers from source to drain. If because of this electric field, what will happen? The drain is actually encroaching in the area of gate, and it will create a channel because of this electric field. Okay. So what will happen? That is why we are calling this as a no, this should be stopped there, and that is why it is called as secondary effect, or some short chain effects are there. So how we can restrict this encroachment? Okay. So we can put another gate on it, and this is the kind of a double gate structure, that you are actually controlling your channel with the help of two gates. That means confine the direction in that way. Okay. This is kind of a double gate, and that will give you the extra benefit or the advantage that we are talking about. There are so many things are there, like now you can play with the things. Okay. All the researchers will do the same thing. Okay. Like you can make two gate different from different material. You can change the thickness of this oxide with respect to this oxide. There are so many number of ways to do the changes, and accordingly you are getting different architecture, different structure with some different applications. So according to the applications, you can tune it. The same thing that we are talking about, but as whatever we are talking about, like another thing is that there are some certain classification are there, like as I told you, symmetric, asymmetric. Symmetric means if you are you are cutting it in from the middle of this channel, then you will see the upper portion and the lower portion will remain exactly same or will behave exactly as same. That will be, we call this as a symmetric structure. If the upper portion is different as a lower portion, then we are calling this as an asymmetric. Like in this case, the gate 1 is of different metal and this gate 2 is of different metal. Suppose here I am using titanium nitride, here I am using aluminum. That will be an asymmetric behavior. Okay? So there are a number of ways to create it. Either you can use earlier you are using SiO2 in this one, now you are using HFO2. One is SiO2, another is HFO2. So it will create different impact on this one. Okay? So you can easily play with some bit changes. Either using the material perspective, from the dimension perspective, everything. So from the process classification, we are defining the double gate into two parts, the symmetric and asymmetric. Asymmetric, whether you are changing the work function, whether you are changing the material means definitely the work function would be changed, or whether you are changing the oxide material or oxide thickness. Okay. Then device classification is there. Earlier the device that we are talking about is a 3-terminal device. Now we have a 4-terminal device. And now can we independently control it? Yes. That will give you another feature. We can independently control it. So earlier, as I already told you, in 1960s, only 4 transistors. By 4 transistors, you can only make one AND gate or one NAND gate. But here, the task of 4 transistors will be completed by only this single one double gate transistors. Okay. There are some additional features are there, but yes, the complexity to control all these things is now enhanced. Okay, all the benefits will come with some challenges, and your main task is to handle that challenges only. Okay, so these are the advantages of these things. But as I already told you, what is the basic thing that we have to take care? Are we able to fabricate it? No. These 3 type of a double gate transistors are there. This is a type 1 where one channel is in between, top gate is on there and other is the bottom gate. Okay. Is it a feasible approach? Can we make it? No, cannot make it. We cannot realize it. Can we make this kind of an structure where source is in at the bottom, drain is at upper, and top gate is there? Yes, gate can be fabricated, but source and drain cannot be made. Okay. Therefore, the solution will given in type 3, and here this structure will be fabricated from gate. We are taking terminal from this side, this side, this side, and this side. Yes, this would be a feasible approach, and that is why this is called as the horizontal double gate, and that is most popularly known as the FinFET. Why FinFET? It seems to be like a fin of a fish. ठीक है, ये इसी हिसाब से लग रहा है जैसा हमने देखा कि एक fish, there is a fish as well, fish body is there and some fins are there. ठीक है, sorry, not good in drawing. ठीक, so these are the fins, these are the 2 different gates are there, these are the channel is there. ठीक, so this is kind of a fish of a fin, and that is why we are calling this as a FinFET. ठीक है, field effect transistor FinFET. So that is the main motivation. So this is come up with this solution, and how you can make it. Obviously, you have to make. There is some certain challenges as well. जैसा मैंने कहा कि चैलेंजेस तो आने हैं, आपको सिर्फ चैलेंजेस को ही रिमूव कराना है, एडवांटेज को लेना है, चैलेंजेस को हैंडल करना है. ठीक, सो हाउ वी कैन डू सो? You can make this kind of structure. Suppose I have one plane is there. One plane is there. Someone told me to put a 2 gate. There is a chance that I can make a gate over there and I can make, but there is a chances that there is some misalignment is there. Like in this case, suppose you have one gate you have made it here, other gate you have made it here. So what will happen? There is a misalignment. So if there is a misalignment, you are not getting the good characteristics. So how you can do so? You can do with the help of this self-aligned gate. And this is the very popular paper, and because of that paper, this Chen Ming Ho, as I already told you, is known as the father of FinFET. The term is coined by himself. While again he termed this as FinFET because in 1989, a similar structure has already been fabricated in 1989. But as the issue is that in 1988 we got this structure will got the popularity. Delta structure, same structure is there. It didn't get any popularity. and who have defined, who have coined this term at the best time, that will be named as the father of FinFET. Okay? So this is the basic scenario. This seems to be a two-gate devices, and that will take all the advantage of double gate devices, which is an easy to fabricate as compared to the planar double gate device. Okay? So there are many options are there. As I told you, in SOI, lot of things are there. You can play with many of the materials. Same thing happened over there. So these are the some fabricated devices are there. This is a gate structure. As you know, there is a tri-gate. There is a channel that the current will flow in this direction, and the gate is wrapped over this channel. So why I am calling this a double gate? Because one gate is there, another gate is there, another gate is there. It seems to be a three-gate. Yes, this is the basic motivation behind the multi-gate devices. Your main aim is to confine the electron from all sides. If you can confine the electron from all sides, you are getting the better current. Okay? The same thing you can do. So the FinFET is not only restricted towards the double gate devices. This can be called as a double gate devices. This is called as, sometimes it will be called as a double gate devices, while we have restrict the impact of third gate because of putting a hard mask or some thickness we have changing. This is again tri-gate devices. Multiple devices can form. As I told you, that most of the researchers will do any of the changes and they will get with some benefits. So these are the things. Also, you will notice that this structure is kind of an rectangular architecture. It seems to be that this is the fin, and this one. This is the thickness, these are the heights of a fin. But now you will see in 22 nanometer, the Intel is able to fabricate this triangular kind of a structure, because it is not feasible to get it rectangular all the time. But TSMC have done this. They make this as a rectangular one. But Intel, both these structures are from the Intel foundry. Intel have fabricated all these devices, but they didn't call this as a FinFET. They again come up with a new solution. They come up with a new name. They call it a tri-gate or a triangular gate FETs. Okay. Although the motivation behind the delta, behind the FinFET, behind the double gate, triple gate, or the tri-gate structure is same. You are getting same. You are doing any changes in the process. You are doing whether it may be intentionally, it may be unintentional changes. Because of the process part, they are able to get it triangular. But they will define this as an achievement that yes, it's a triangular part. Okay. So this is kind of a lot of researcher has been gone through. As I told you, there is a tri-gate structure is there. One more, they are making some sigma, some ohm structure. This is gate all around. The gate is wrapped all sided. This is a gate all around or a cylindrical or a structure. If this so this is an, as of now, this is an cuboid. But if you make this as a cylindrical architecture, this is a gate all around or a cylindrical architecture, or sometimes we call this as a nano wire. So there is a no ending list of multi-gate devices. Lot of the devices we can able to fabricate. As you know, as I told you, that fin can be rectangular, fin can be triangular, and fin can be in diamond shape. This is all because of the process parameter. But yes, again, lot of research has been carried out from the FinFET. It will take a large boom on the research towards the FinFET devices. But still, the FinFET device also have many challenges. Okay? Like more. This is a three-dimensional device. Definitely, it have a more parasitics. More parasitics are there. So you have to make a fine balance in between the short channel effect on the parasitic resistance. Okay? So there are some certain challenges are also there. The most important part is the corner effect. Why corner effect is there? Can you make this kind of a structure? If you are making this kind of a structure, at this part, you are applying some potential. So this will be a premature inversion. So that is why it is suggestible to make it as a corner device, a rounded corner. Okay? So these are the corner effect. Means all the new devices come up with new challenges. You have to handle it. You have to use it for some particular application. Okay? So this is the base. And the major disadvantage is with quantization. The major advantage of a normal MOS device is actually its width. You can suppose width W/L parameter is very important parameter when we are making any of the circuit applications. Length is actually fixed by the technology node. Let it be. So I'm giving you an example. Suppose I'm taking a 45 nanometer device. That means the length is nearly about 45 nanometer. So whenever you are picking any kind of a technology, the length would be fixed. Then what is the next parameter that you can play with? Suppose you want that much current, and current is directly proportional to W/L, and L is fixed. How you can increase or decrease the current? With the help of width. So in that case, you can enhance the width. Either you can take width 1.2 nanometer or 120 nanometer. Let it be any random value I can take. 125, 130, 137, any of the value you can give it to. Nanometer or micrometer is in the range. Most of the time we are taking in the nanometer region because as you know that device that we are dealing about in the sub-nanometer region. But here, the thickness, in case of a FinFET, what is the width? The clear definition is that whatever we enter the gate is called as the width. And what the width is? This plus this plus this. So, if this is the width of a one fin, then you can only add multiple fins. If this is the width, W, then if you wanted to increase W, then you can only go with 2W or a 3W or a 4W, depending upon number of things you can increase. But you cannot make 1.5 of W. You cannot make 2.7 of W, 2.7 times of W. No. And that feasibility will be at the MOS side. And this is the biggest challenge in the FinFET devices. And that is why we came up with a new solutions. As of now, the Intel is talking about, sorry, I'll skip this part. So this, another challenge is that the nano sheet devices. So these are the basic from your understanding. I'm just giving an example. These are the basic part. Initially, you are at the MOS devices. This is my MOS devices that have a physical limit because of the scaling. Then you do some changes and taking the help of SOI devices that give you an additional flexibility in terms of speed. Then again, you are approaching towards some of the parameters will not be getting as per your requirement. Then you go with the double gate devices. Then not feasible to get this double gate devices. Okay, and move it to the FinFET devices. This is an SOI FinFET. We are taking the advantage of both the SOI device and the Fin devices. But again, this is a 3-tunnel. You are confining the gate. You are confining the channel from 3 sides. Can you do it from the 4 side? Yes, you can do so. In gate all around means nano wire devices. It may be a cylindrical architecture. It may be a simple architecture. Okay. So that will be a thing. But yes, there is on both this FinFET and the nano wire device. Here the width is quantized, and therefore currently from past 2 to 3 years back, the Intel is come up with a bit changing devices that they call it as a nano sheet devices, where they are getting the advantage of enhancing the width and the fin. Okay. So this is the case of a devices. This is called as the nano sheet. While the good thing about this device is that most of the researchers will work towards it. They call it as a nano sheet because there are multiple sheets are there, and they all are in nano dimension. So they used to call this as a nano sheet. Or Intel will again come up with a new name. As I already told you, in case of a FinFET, they come up with a tri-gate or a triple gate structure. Okay, triangular gate architecture. But in this case, they will call this as a ribbon FET. So yes, there is in today's trend. They come up with a new dimension. There are multiple structures are there, like CFET is there, and someone will call this as a fork sheet, or sheets are there. Okay, like fork is there, like you आपने ध्यान भी दिया. So this is kind of a fork is there. So there are multiple things are there. So presently we are working towards this devices, or Intel is working hard to devices, and it is expected that up to 3 nanometer region, up to 3 nanometer technology node, we will restrict it with this devices. So as I already told you that after 10 nanometer, what we have to think about what beyond the silicon. But now the limit will be extended up to at end of 3 nanometer. So now at 10, if we wanted to make any devices less than 3 nanometer, we have to think about it. So presently, this is the basic part. These are the all advantages that we are talking about. I'm not going into detail. So in that part, so whatever be the disadvantages associated with the FinFET, that will be taken care in the nano sheet, okay, or a ribbon FET. And these are the, yes, any devices come with again some complexities are there. So instead of making this devices, they are making a stack nano sheet devices. So depending upon the number of increasing the number of stack, you can go up with a different width. Okay. So these are the different devices which have a gate all around architecture, as well as, or you can say it is sum up of all these devices that we have. So it is not in only in the phase, it is actually the Intel and Samsung is working hard to commercialize it, and Samsung told that they will put all these things in the DRAM packages, and on the DRAM they will trying to make. So they wanted to, they will very soon, they claim that they will very soon commercialize it in 5 nanometer devices. So I cannot comment as of now what are the country status. So if yes, most of the working industries are working hard towards this. So this is the case. So this is not a hypothetical concept. These all are the fabricated devices by the Intel and Samsung and all these things. So hope this. So overall, multi-gate is a good part, and yes, it will be sub nanometer devices, sub 7 nanometer devices. We are looking towards all these multi-gate devices, and yes, we have to think about it, because parallel research is already going on at how we can use the spin devices, how you can use the spin logic or photonics, how it can help that like because there are so many things associated with the silicon or germanium. You have to associate with that. Only the things you have changes, but ultimately you have to move up within edges of the silicon. You have to opt some new material in that in near future. So that we will look about it. So that's all from my side. If you have any doubt, you can ask me.
So candidate, if you are having any doubt, kindly ask. Repeat again. If you are having any doubt, kindly ask. So I think no doubt is there.
Okay,
Online में generally doubt रहते नहीं है.
okay, so all that for the time being, I'll share the slides with you, Ashish sir. So you can share it with the participants, and if they have any doubts, you can share my contact details with them, so they can contact me in case they find it.
Thank you, Dr. Pankaj, for providing your wonderful talk on FinFET-based devices. So, you have covered the latest trends that are available in the devices and the nanoelectronics. So, thanks for this talk, and thanks for accepting our invitation. So, thank you. Thank you very much.
Thanks, sir. So, shall I leave, sir?
Yeah.
Okay. Thank you, sir. Thanks.
So, candidate, our next talk will be started on 1 p.m. Okay. So, you please join at 1 p.m. this link. Thank you.